Good afternoon, everybody. It's my great pleasure to have Victor Martin Lozano with us, who is known probably to nearly all of us because of his long and successful stay at the IFT. Currently, he is, after being postdoc in Bonn, he is now postdoc at DESY in Hamburg. And actually, we also started some work there together with a group there. But today he will speak about ongoing work already for quite some time with Ernesto and Anibal y Nicolás Mileo. Victor, please, the floor is yours.
Thank you very much, Ben. Hi, everyone. First of all, thank you for inviting me and giving me the opportunity to give this seminar here in IFT. It's always a pleasure to come back, even if this time is virtual. But it is the first time that I can give a seminar in the IFT, so it's kind of a special occasion for me. So let's start with the seminar, and I'm going to talk about this work that we have been doing for some years now. So basically, the title is Scalar Taus at the LHC, how we will find them. And the title could sound a bit ambitious because I'm speaking about the future, how we will find them. But I like to see this as something with a little bit of hope more than ambitious. So basically this work is in collaboration with Ernesto, that is there in IFT, Aníbal and Nicolás, that are in La Plata. And it's based in a paper that we published 2 years ago, and now another one that is coming this December, hopefully. Let's see. So basically, we know that the LHC has been running for almost 10 years. We know that it has run not at every moment, but almost a lot of time. And well, we know that the LHC has been recording some information from different runs at 7, 8, and 13 TeV data energies. And well, we have a lot of information about the events that have been produced there. And for example, the last run, the last one that we have information, the LHC has delivered more than 130 inverse femtobarns in data that could be used for searches. That is something really incredible, because for example, for the other runs at 7 and 8 TeV, this luminosity was not able to be reached. So despite the fact that we have recorded a lot of data, we have only found one new particle, something that is like, well, the standard model Higgs boson, no? Let's call it standard model like Higgs boson. This particle has been found and measured, and it has been found that its mass is around 125 GeV, and this has been measured in different channels and for the 2 different experiments, Atlas and CMS, with a good precision, as we can see here. Furthermore, the signal strength of the Higgs, the standard model like Higgs boson, has been measured, and this signal strength basically compares the production cross-section and the decay of the Higgs into the different channels with respect to the standard model Higgs boson. And as we can see here, some of the channels are measured with extremely high precision, while others like Higgs 2 mu mu or Z gamma are still improving. But if we combine all the measurements, we can see that the signal strength of the Higgs boson into standard model particles, it's quite similar to the one of the standard model. Still, there is room for new physics, since the measurement is a bit away of the standard model value, and even taking into account the errors, one can see that there is room still for new physics. But we haven't found anything else apart from the Higgs boson. So other searches concerning the Higgs boson have been performed, like double Higgs production. That this is basically a way to unveil the electroweak symmetry breaking sector, since we can know, for example, the triple and quartic coupling of the Higgs. So different searches such as BB bar tau tau, BB bar gamma gamma, or 2Ws plus photons have been performed, but still we are far from having enough precision to say something about the electroweak sector. Apart from that, there are lots of searches that are looking for new particles, new models beyond the standard model. So for example, this is a summary of all the searches that Atlas has for exotic. So this means models that are not supersymmetry. And we can see the limits of all the particles, or let's say the scale of the theory sometimes. For example, for extra dimensions, the limits could go from almost 2 TeV to almost 10 TeV. For extra gauge bosons, even we can reach 5, 6 TeV. And if we go to leptoquarks, the limits are around 1 and 2 TeV. So the hope of finding some of these particles at lower values of the mass is a bit difficult. And we can see also that SUSY searches are suffering the same problem. Basically, LHC is looking for SUSY processes and SUSY particles. And we can see that for colored particles, the limits are really, really strong in that sense. They reach 1 up to 2 TeV for gluinos and squarks. If we go to third generation of squarks, the limits are a bit weaker. And if we go to electroweak, electroweakinos, that are neutralinos and charginos, the limits are a bit weaker, but still these limits are increasing the mass of the particles. So basically what we have is a landscape that could be a bit not full of hope. So I want to see this as this image, right? I mean, the particle physicists are sitting in that bench while all the building is basically being destroyed by the LHC. But I want to give here a bit of hope, because sometimes new physics could be hidden. Basically, I will focus on the Higgs sector and also some particles of the supersymmetry spectrum. So basically, when a standard model like Higgs boson was discovered in the LHC, there is a natural question that we physicists could ask to ourselves: if the Higgs sector is just the boson found in the LHC, or maybe there are several more states that one can find. Why that? Well, we know that in theories when I mean that implied some SU2 doublets, and we make them mixed because they have the same quantum numbers, we find different spectrum that could basically lead to different Higgs states. For example, if we have a theory in which we introduce 2 SU2 left doublets, usually what we have in the Higgs spectrum is something like this. We have lighter Higgs, CP even, and neutral, CP even heavier neutral Higgs, a pseudoscalar, and a charged Higgs. And this kind of a spectrum is really present in different models, such as the typical 2 Higgs doublet model or supersymmetry, like the minimal supersymmetric standard model or the next to minimal supersymmetric standard model. It is true that in this case, in the NMSSM, we have to include a singlet, but the SU2 left doublets could give, will give this spectrum as well. So basically, if we compare with what we have found in the LHC, we can think that the standard model like Higgs boson could be, for example, this one, the lighter one, and still we have to find the other Higgses, the other states. So as these theories have been proposed in the literature for so long, Atlas and CMS have searches for basically looking at for these heavy states, not only the neutral ones, but also the charged one. And these final states of the heavy Higgs are usually the ones that I write here. So the heavy Higgs will decay into Ws, Z bosons, or tau leptons. Basically, I think there is, well, the experimentalists do this because they know the standard model really well. And also, if one studies the properties of this heavy Higgs boson, the main decays of these ones are the decays that are present here. So what experimentalists basically do is impose constraint on these decays when they are looking for them on the parameter space of the different theories. So basically what they take is two Higgs doublet models or MSSM, and they impose constraint on the parameters of these theories. And the most important ones that could play a role in the Higgs sector are MA, that is the mass of the pseudoscalar, and tangent beta. So for example, we have here a search that is looking for Higgs going to 2Ws from Atlas. And we can see that they impose basically constraints on MH, the mass of the Higgs, and tangent beta. In this particular search, the interpretation is within the two Higgs doublet model, type 2, but it is quite easy to translate this data into the MSSM. And as we can see, this search is able to exclude values of tangent beta that are low and values of MH that are also low. However, if we go to the different channel, that is, for example, a Higgs decaying into 2 tau leptons, the picture is very different, because now what we can exclude are the large values of tangent beta for different masses of the pseudoscalar. Here as well, I mean, the interpretation is within the MSSM, but it is easy to translate all this data into the two Higgs doublet model, for example. So here what we have is that large values of tangent beta are covered. This is basically because the Higgs sector couples differently to the gauge bosons and the fermions. So now if we look, for example, for charged Higgses, there are also searches performed by Atlas. And here we can see that they can cover different values of tangent beta and the mass of the charged Higgs. And one can think, well, this is also another search when there is a double Higgs production into different particles of the standard model. So we see that Atlas and CMS are putting some effort in finding a heavy Higgs or heavy Higgses, but as we see, they are all based on standard model decays. But we can ask why they are really focused on MA and tangent beta. And this is basically if we go just to a simple model in which we add two SU2 left doublets, we can basically write the Higgs states as a function, well, of the mass eigenstates, doing basically a rotation. This vector here is the one of the webs of the Higgses. So basically, tangent beta is defined as the ratio of the two webs of the Higgses. And now the eigenvalues of the masses of the Higgses are given by this formula. As we can see here, there are two parameters that are not known, and basically are MA and tangent beta here. That's why it's so important that all of these results are written in terms of MA and tangent beta, because if we know them, we can know the masses of the two Higgses. When we take the limit that MA is greater than the mass of the set boson, it is easy to see that the coupling of the Higgs boson, heavy Higgs boson, to the down type fermions is basically proportional to tangent beta, while the Higgs coupling to the up type fermions is proportional to the inverse of tangent beta. And this is, if we have this in mind, we can understand why in the search of Higgs to taus, the LHC is able to cover areas with large tangent beta, because it's the area where it's going to be, the Higgs is going to couple more to the tau leptons. So for example, in the search of the Higgs to tau, we can basically put these limits, because we can think that the Higgs in this region here, that is large tangent beta, is going to be produced through BB bar, and then it will decay into tau plus tau minus. And this is why the large tangent beta area is covered. However, basically what we have seen here in all these searches is that the experimentalists are assuming that the heavy Higgs is going to decay into standard model particles. So what happens if we have a theory that not only includes a richer Higgs spectrum, but it also has some new particles, let's say supersymmetry. In supersymmetry, we have particles that could be lighter, like neutralinos, for example, and can couple to the Higgs. In this case, what happens when these, for example, these decays of the Higgs to new particles are available? So for example, for masses of 1 TeV, we can find some Higgses decaying into neutralinos or staus, for example. So basically, these searches are not covering this information, and still the limits that are imposing is basically neglecting these decays. So we can think that when light particles coming from a new theory, new model that we have come to the game, come to play this game, the constraints that are imposed by LHC are actually weaker than the ones that they are telling us. So basically there is still room to find new particles and something beyond the standard model. So for example, let's take this work done here by Aníbal and Michael, in which they play a bit with this assumption. So they took the previous search, this one. So they plot it in gray here as a function of tangent beta and MH. And they studied some points within the MSSM in which the Higgs boson is going to be tested against this search. So in the MSSM, well, we have that the coupling of the Higgs boson to the tau leptons is proportional to tangent beta, but the heavy Higgs boson is also going to couple to the down type fermions that could be staus or spotons. So this coupling is proportional to SUSY parameters like mu and the trilinear coupling of the down type fermion, and also to the mass of the fermion, and also tangent beta. So if we play with these parameters, we can find points in the parameter space that could play the next game. So when we are basically increasing this coupling using, for example, mu or the trilinear coupling, we are going to enhance a bit the branching ratio of the Higgs into, for example, in this case, the scalar taus. So when we are increasing this coupling, the others branching ratios that are present in the Higgs sector are going to decrease a bit. So basically what we have here, all the orange points are the ones that has that have a value of the trilinear coupling that is different from 0. So this coupling is going to be enhanced. And the ones that are falling inside the gray region that in principle are going to be excluded, they are basically not. And this is basically because the branching ratio of the Higgs to the tau leptons is decreased in such a way that the search is not powerful enough in order to constrain it. So basically what we have done is to increase the branching ratio of the Higgs into new particles so that the Higgs into standard model particles is decreased and is not able to be covered by the LHC searches. So as we are playing this game, we can think that we are opening a new channel. In this case, the Higgs going to taus. And such a new channel deserves a new study because we are looking for these kind of searches, Higgs to a standard model. But now that we have opened this one, maybe it is worth looking for it. So let's see what happens when we have tau lepton, tau, sorry, within this SSM, and they are connected to the Higgs sector. So basically, the couplings of the heavy Higgses to the dumb type fermions are like this. We have the coupling of the CP even state here and the CPO state here, coupling is here. And we can see that they are coupling more or less the same, except for one sign in mu. And they depend on the mu parameter and the trilinear coupling of the down type fermion here. So one can find points in the parameter space.
Can I ask a question?
Sure.
For the capital H, you would also have the diagonal couplings, no? Tau left, tau left, tau right, tau right. Are they always suppressed with respect to these couplings in your analysis, or?
They basically are proportional to the mass of the fermion. And
they have the Yukawa part and the electroweak part, yeah?
Yes.
And the electroweak part is then stronger than the one to the fermions. But I don't know how it compares because you have a tau large and tangent beta large, I suppose, exactly. So may always be dominating.
In principle, they are the ones, I mean, the other ones, we also take them into account, but as we are playing with these parameters here, and we have A large and tangent beta large as well, as you said, the main contribution would be from the left-right coupling. But you're right, I mean, okay. The diagonal ones are also there.
Okay, thanks.
But we play with the non-diagonal ones in order to get the branching ratios as we are saying here. So basically playing with these ones, we can enhance the branching ratio of the Higgs into taus while reducing the one in taus. So the tau mass matrix is defined as it is here, and when we diagonalize it, we obtain two eigenvalues here. And basically we can parameterize the lighter state of the tau and the heavier one in terms of the left-right components through this angle here, tangent to theta, that is defined with the the numbers in this matrix. So having the light and heavy state of the staus, we can see how they couple to the Higgs. So basically the decay width of the Higgs into staus is given by this formula, where lambda is the typical function that appears in the decays. And now we see that we have the coupling of the Higgs to the stau mass states. And in order to connect the coupling of the Higgs to mass states, basically it is connected to the one of the chiralities using a rotation here. So basically the expression of the mass states, the coupling of the mass states is depends on the couplings that we had here before. So they will depend on A, mu, and tangent beta. And having a look at the mass eigenstates, we have defined two scenarios that could be interesting. Scenario one, that basically the mixing angle is maximal. We have theta that is p/4, and we have m tau 1,2 large, and we have m tau 1,1 and m tau 2,2 that are of the similar, they have more or less the same order. So this will basically produce a cancellation of the contribution that mixes the chiralities. In that sense, the ones that are GH state 1, and state 2 are enhanced, while the ones that mix, in this case, chiralities, and the one that mix coupled to the odd Higgs are going to be suppressed. In this scenario, what we have basically is that the decays of the heavy Higgs into the same mass eigenstate are enhanced. But as we have usually large values of STAU2, then the Higgs decaying into STAU2 are not kinematically allowed. So usually in this scenario one, what we have is the Higgs decaying into two light states of staus. In scenario two, what we have is that the mass eigenstate could mix the chirality, and well, what we have basically is the opposite. Now here we have Higgs decays into the different type of staus, combination of 1 and 2, 2 and 1, and also the CP odd Higgs play a role here, the pseudoscalar. So in this case, we have more variety on the decays. So basically, in order to study the two scenarios, we have performed a collider study. And what we ask basically is for two opposite sign tau leptons plus missing energy coming from the neutralinos. So basically what we are producing, as we are going to take the large tangent beta regime, is that the production of the Higgs sector is going to be through BB bar, association of BB bar. Then they will decay into a couple of staus, depending, these staus will depend on if we are in scenario 1 or scenario 2. And then the staus will decay into a tau lepton and a neutralino. So we will have two taus with different sign and a large amount of missing energy. So in order to set an analysis that could be used for this channel, we picked two benchmark points for both scenarios, for each scenario. And we have chosen an MA that is more or less similar in both of them. It's more or less 1 dB. We chose a tangent beta that is large, 30, almost 34 for scenario 1 and 45 for scenario 2. We choose an M1 that will give us a mass of the neutralino of almost 100 GeV. And then we choose mu negative and large, and also the value of the trilinear coupling to taus also large. And the values of the staus in both scenarios are almost 350, 370 in this case. And for the heaviest state of the staus is 400 in scenario 1 and almost 600 in scenario 2. With these numbers, this channel here will have a total cross section in a scenario 1 of 31.7 femtobarns at 14 dB. This is including all the production and decays. And the branching ratio of the Higgs into staus is almost 20%. In scenario 2, we have 13.2 femtobarns at 14 dB. And the branching ratios are slightly greater. For the pseudoscalar is 25%, and for the Higgs is 22%. And well, basically, in order to produce all of this data, we have used Spheno, and then we have calculated the cross section is in SUSY, because it calculates things at next to leading order. And in order to perform the collider study, we have used MATGraph. What we want basically is to study this channel here. So we have 2 taus and missing energy. So basically we apply some basic cuts in order to select the tau leptons. So we select that the first tau lepton should have more than 50 GeV as transverse momentum, while the second one will have something, a transverse momentum that is greater than 40 GeV. And the pseudo rapidity is taken as a usual value in order to fall into the barrel of the Atlas and CMS experiments. So the main processes of background are these ones appearing here in this table that are TT bar, W plus jets, Z plus jets, WW, and Z. And we can see here the numbers of the cross section that are pretty high in comparison with the ones that we have here, right? I mean, this is of the order of 30, 13 femtobarn, while here we have some really large numbers. The multi-jet background is also a contribution to the background, but when we take, we require that the bands should have some large amount of missing energy, this multi-jet background disappears immediately. So as we have missing energy in the final state, we can employ some kinematical variables that make use of it. So for example, we have the transverse mass that will use the PT of the taus and the missing energy, and the so-called transverse mass that will play with the role of the missing energy. And usually this kinematical variable here is used when one has 2 sources of missing energy that we cannot basically see in the detector, but we know that they are there. For example, in the case of SUSY, we have 2 neutralinos. And we guess here more or less how much missing energy will contribute. So basically, we play with all these variables in order to compare them with the different background. And we have plot here all the distribution of the signal and the background. The signal basically is in black and dark red here, and the background is in different colors here. So for the transverse mass of the tau 1 and the second tau, we can see that the signal has more events for large values of transverse mass of both tau 1 and tau 2. So for that reason, we choose a cut that basically is the transverse mass should be larger than 120 GeV. So for 120 GeV, we get rid of these peaks here appearing in Z plus jets, W plus jets, and here as well. Then we can go to the invariant mass of the taus, and we can see that the main number of events comes from the Z plus jets. So we can see here that this peak belongs to the Z boson. So if we take an invariant mass that is greater than 100 GeV, we are getting rid of all these events appearing here. And last but not least, we are using MT2 variable here. And as we can see, this is the most powerful kinematical variable, because if we take this variable to be larger than 150 or even larger values, the signal is not really affected, but the background basically drop down. So we can take this variable to be greater than 180 GeV in order to get rid of the background events. So our signal region of this channel would be this one. We select two opposite sign taus. We require that there are no big quarks, because if we include big quarks from the big quark production, could be a bit more, it's a bit messier. And we didn't want to take this challenge yet. And then we take all the cuts that are here. So we compute the significance of a point using this formula here, that it is taken when there are some errors, here, some uncertainties in the background. If we take the limit when these uncertainties are going to zero, we recover the typical discovery formula. And we can conclude that the point is excluded at 95% confidence level using this formula here. So let's see the result of our benchmark points. So when we have no cuts, the discovery significance is basically negligible in both scenarios, but we take the signal region that we used, we can see that we reduce the number of events significantly. In that case, we can get some discovery significance of 6 and 5. So we can have a discovery. So now that we basically check that our analysis is useful for this channel, we can see the results that we obtain. Basically, we took scenario 1 and scenario 2. We simulated points in both of them, and we tested against our analysis. So for scenario 1, we did a scan of 27 points, and we checked the exclusion power of this channel for a configuration of the LHC of 14 TeV and 100 inverse femtobans. In this case, the orange points are excluded while the blue ones are still allowed. So the search is not powerful enough to exclude these points. We can see that the most of the points are excluded for not so large masses of the Higgs. This means that the Higgs is produced, and we can see it with our search. This point here is also excluded, even if it has a large value of the mass of the Higgs, and this is due to the large tangent beta value. So the coupling is enhanced such a way that the production is also enhanced. And even if it has a mass of the Higgs boson that is large, we can exclude it. These points can be seen also in the trilinear coupling plot, and we have more or less the same. For small values of the mass of the Higgs, we can exclude all these points, while when the Higgs is larger than 1 TeV, we are not able to do it. Only we can do it when they have a large value of the trilinear coupling. We can do the opposite and see the discovery potential. And the green points are the ones that could be discovered for a configuration of 14 TeV and 100 inverse femtovars. In this case, it's more or less the same. For low values of MH, we can see that we could discover these points. However, when we go to further values of the mass of the Higgs, we cannot do it. In this case, we can see the same for values of the trilinear coupling. And basically what we cannot find is what it is far from the mass of the Higgs of 1 TeV. So what we can do also is to take all these points and basically make some prospects of exclusion in the plane of mass of the Higgs and tau masses. And we can see that for 100 inverse femtobarn at 14 TeV, we can exclude all the dark gray area here. That means that we are able to exclude low masses of the Higgs boson, but we are only able to exclude large masses of the taus. This is because when we have a Higgs boson of a mass, I don't know, for example, here 1 TeV, and we have smaller taus, the taus are going to be very boosted. So our analysis cannot distinguish very well the missing energy and the neutralino, the taus are going to be back to back, and then the amount of missing energy is not high enough, it's not large enough in order our analysis to be powerful. So in some sense, our analysis require large masses of the taus in order to not to be boosted by the Higgs decay. And when we go to 1000 inverse femtobarn, we are able to exclude all this region that was not able for less data. We can make the same for discovery, and we see that we can discover in a configuration of 1000 inverse femtobarn, we are able to reach more than 800 GeV Higgs, but for high values of the mass of the tau. When we go to larger values of the mass of the Higgs, basically we cannot see anything for low values of the mass of the tau. We have the same problem, but for discovery. If we go to scenario 2, here we have simulated 228 points. And here we plot the points. Orange ones are excluded while the blue ones are allowed. In terms of, we have plot in terms of MA and the trilinear coupling for a configuration of 1000 inverse femtobarn at 14 TeV. And we can see that for larger values of the trilinear coupling, the points are excluded, while the ones that present smaller values for the same mass are still allowed. The same happens if we compare this with tangent beta. When we have large tangent beta, all the points are excluded because all the couplings are enhanced, and so is the cross section. While for lower values, we still have some points that are still allowed. We can see the same in the discovery plot. We can see that the ones that are the points that are discovered are those that have larger values of the trilinear coupling and larger values of tangent beta here. And here we can we have plotted another variables. This one is as in scenario 2, we have the two states of the taus playing a role in the decays, and they have different masses. We can plot the mass of the pseudoscalar against the average mass of the taus. So if we do this, we can see that we are able to exclude average masses of the taus that are greater than 260 or more, while the ones that are low we cannot see. I mean, our analysis is not powerful enough. And if we plot this against the difference in masses of the stars, we see more or less the same. What it is important here is that the average mass of the stars are large, as we saw in the scenario 1, that the stars should be large in order to be excluded or found by our analysis. The discovery plots are more or less the same. We find discovery or evidence if we go to masses of the average masses of the stars that are greater than 300 GeV, while the ones that are lower than this value are cannot be really found with our analysis. So if we plot a similar plot as in the scenario 1, but here instead of the mass of the stars, we plot the average mass of the stars, what we can see is that we can exclude for 100 inverse femtobar or 1000 inverse femtobar stars that are greater than 260, 270 GeV for masses of the Higgs boson that are greater than 850. When we have masses below that value, we can exclude all the parameter space. And if we go to the discovery plot, we can see that for 100 inverse femtobarn, we cannot go further in masses of the Higgs boson. Here, for example, we see this line going up because we are not able to see this. And we have to go to values of stars that are really large in order to discover something. If we go to 1000 inverse femtobarn, what we can see is that for masses that are greater than 300 GeV, we can cover all the parameter space, while for masses that are lower than 300 GeV, we are only able to constrain Higgs masses that are lower than 820 or something like that. So basically, this is how our analysis work. Looking for new particle decays into the Higgs sector. And I come to my conclusions. And basically what we have is that in many beyond the standard model theories, the Higgs sector is usually extended. It presents new states that could be heavier, could be lighter, and could be not even the same CP as the one found in LHC. LHC is now looking for them, for these new states, but usually what they do is to rely on the fact that these heavy states will decay into the standard model particles, the standard model sector. But they don't take into account that they could also decay new particles that could be there. So if one considers these decays, the constraints that are now in the market, the ones that Atlas and CMS are giving us, are weaker. And also it makes sense to cover these new searches, to do an analysis as we have done here. And we have developed a search for stars as a final state. And we have a resonant heavy Higgs decay. And we saw that for 14 TeV LHC at 1000 inverse femtobarn, or even at 100 inverse femtobarn luminosity, we can we are able to cover the parameter space that are basically stars greater than 250 GeV and masses of the Higgses that are smaller than 900 GeV. So not only I wanted not only to say some conclusions, but also open questions that I think they are interesting these days. So having this kind of channel is, I would say, a win-win discovery if they are found, because you don't only find a Higgs boson, but also new particles as a final state. But now some other questions appear, right? I mean, are we sure we are measuring the model we want, or maybe there is another one that mimic the same channel, right? So one can also imagine other channels and look for them in such a way that one can have an overview of all the properties of this new heavy Higgs boson, and so on. And also, for example, regarding our analysis, we have two Tau states and we have two scenarios. And how can we be sure, if we have this kind of channel, that we are measuring scenario 1 or scenario 2? So are there some differences, and is our channel good measuring these differences? And basically now, I mean, what we have when we are exploring BSM theories, and particularly the Higgs, how can we, I mean, the most important key here, I think, is to modelize the heavy Higgs sector that could be in some sense model independent in such a way that all the channels or all the signatures that one can find in the experiment can be traced, and somehow the experimentalist could translate their data into these, I would say, toy models or effective models in such a way that every phenomenologist with their favorite model could take all the information and basically paste it in their model. So the experimentalists, they don't have to give a specific model or constraints into a specific model, but in this kind of toy or toy models. So all the BSM people could take all the information from there. But this basically is something that is my opinion. And I think we as a community should move in this direction more than, we can also work in different models, right? But I think we have to communicate better with experimentalists somehow. And basically this is my talk. Thank you.
Thanks a lot, Victor, for this very interesting talk. I would say even very close to reality, yeah? Very collider-oriented.
Yes, yes.
Thanks. Are there questions or comments for Victor?
One question. Hello, Victor.
Hi, Carlos.
So you are assuming that the tau is the next to LSP, no, in this computation?
Yes.
Okay. And the tau, you take the, I mean, you take a tau, not the muon or the electron because of the couplings, I guess, no? Because you need large couplings to.
Yes, exactly.
Okay. Okay. And in principle, you could apply this idea to other SUSY particles, no? If you assume that instead of the tau, the next to LSP, you have other particle also next to LSP, similar analysis, no?
Yes, exactly. I mean, this could be applied to other ones. So, for example, I mean, we use this one because tau were easy to do the analysis with taus in the final state. So, for example, one can use bosons if one wants this, but maybe it could be messier. I don't know. I mean, we did it because the analysis was easier for us, and we found that the taus could play a role as NLSPs. That
Well,
could be interesting.
There's bottom, maybe there are bounds, no, which
Yes.
maybe is too heavy. But I don't know. I mean, neutralinos, no? You have neutralinos, which could be still light, no? And
yes,
so,
there is a paper that they took this into account, but they didn't do an analysis, a collider analysis on this. I think it's from Stefania Gori. and collaborators.
Yeah.
They take into account all the heavy Higgs decays into MSSM particles, like neutralinos, charginos, and so on.
There have been several attempts over the years by Atlas and CMS to develop analyses for the heavy Higgs searches decaying into charginos and neutralinos. And they all, in the end, led to very few, if not nothing. And I think the main reason was that the background depends on the SUSY parameter point, and then it becomes computationally very expensive to simulate it. Yeah, and so I saw various groups that tried it and in the end didn't got to a result. So to have a real search developed for the heavy Higgs decays into charginos neutralinos seems to be complicated to do it thoroughly. Yeah.
Mm-hmm.
I mean, I gave a talk about this in there in DESY, and they were really, the experimentalists were really interested, because they said that they have been using always heavy Higgs into standard model, and they wanted to change it somehow, but they were a bit lost. This is what they told me.
More questions for Victor? Maybe I can ask a question, or maybe first a remark and then a question. Can you go one slide back? Yeah, the second point. I think the situation is not as bleak as you depicted here. I mean, normally the experimentalists present their results in two ways. First, a more model independent one, and then the model interpretation. And the model independent one, they do it, for example, exactly for this channel that you were looking at, BB to Higgs, Higgs to tau tau. And they do it even together with the other competing channel, GLU to Higgs to tau tau. And if you know how to do it, you can combine the two and map exactly your model to this combination of the two production channels and say whether a parameter point is excluded or not. The experimentalists, they provide a three-dimensional map. One dimension is the mass, the other two dimensions are the two production cross-sections, and then they give the likelihood in this three-dimensional plane.
Yeah, like Higgs bounds.
Yes, Higgs bounds
right.
has this included, yeah. So in this sense, one can easily check whether a point, also points that you are looking at, are excluded, or how far away are they from the exclusion. So I think this problem is effectively solved, luckily. Otherwise, if we only had these model-dependent limits, we wouldn't know anything, as you pointed out correctly. My question, how strongly suppressed is the branching ratio, heavy Higgs to tau tau, in the benchmark points that you were looking at? Because when I look at the latest limits from Atlas in the MH21, MH125 benchmark plane, for 1 TeV, values of tangent beta above 8 or so are excluded. And I'm surprised that your values of 30 to 40 are not excluded. You must have a tremendous suppression of the branching ratio there.
Yes, the thing is that it is true that some of the points that now, I mean, that we found now are excluded by this search.
Okay.
I mean, when we started this, some of them were in tension with the data. But now that we have 100, almost 40 inverse femtobarn, we're in that sense a bit, yeah.
But do you know the branching ratio to tau that remains for your two initial benchmark points?
I cannot remember now.
If you don't know now, just if you could look it up and send it to me, I would be curious.
Sure. I guess that the one of scenario 1 is totally excluded, I guess, because it was in tension with the data. So I guess that now with more luminosity is now excluded.
Yeah.
But what we tried to show here was more like a way to find the staus. So
I find it very interesting. And I mean, you could always escape to go to higher masses, where the limits are less strict, of course, then the production cross-section goes down as well, and you find less signal events. So it's a trade-off that one would have there. Yeah. More questions or comments for Victor? No? Okay, then I say thank you again for this really interesting talk. And I hope to see you at some point in 3D again. Yeah.
Yes, I hope so.
I will stop the recording.
Yeah.
Yeah.